Courses in the cement industry. Present to you. In this course will be explained Rotary kiln drives. Part 3. Covered in this section. Tooth profile, backlash clearances, module of a gear, temperature measurement, surface roughness, and lubrication. In this picture it is explained. Tooth profile. Tooth profile also important is the longitudinal relationship of the gear relative to the pinion. Also see this video. We follow together. Tooth profile. See this picture. Tooth profile wear. 1. If a rotary kiln runs in one position, for a long period of time, the gear teeth will develop a wear pattern, based on this position. When the rotary kiln shifts to a new axial position, the gear also changes its position relative to the pinion, and a new wear pattern begins. If the existing pattern is severe, this will create a greatly reduced contact area resulting in extremely high pressures. In many cases this extreme pressure will be high enough to cause the lubrication to squeeze out and become ineffective. This leads to high sliding friction and aggressive wear of the tooth profile. 2. The operator may see a high surge in the drive motor amps for the period of time it takes to wear, so the load is again spread across the entire width. During this process, the portion of the tooth experiencing the high stresses may also experience spalling and cracking. As a result of this aggressive wear, the lubricant will be contaminated with metal fragments and shavings, creating a high potential for increases in wear on other areas of the teeth. In this picture it is explained. Tooth profile. 1. Mesh, pitch circle. Measurement backlash and root clearance of pinion and girth gear mesh. We follow together. Tooth profile. In this picture it is explained. Mesh, pitch circle. We follow together. Tooth profile. In this picture it is explained. Backlash. Backlash clearances. 1. For mills and rotary kiln drives, the differences between the temperature when gears are set, and the operating temperature must be considered. 2. The table beside shows the amount of backlash recommended for various temperature differentials and sizes of gears. 3. The alignment must be as accurate as it is practical to achieve. Important note: make adjustments as soon as any misalignment is detected. We follow together. Tooth profile. In this picture, it is explained how to measure method mesh, root clearance. In this picture it is explained. Root clearance, top clearance. In this picture it is explained. Root clearance, bottom clearance. Clearance. Girth gear backlash and root clearance, measured in cold conditions. Tolerances. Girth gear and pinion teeth clearance, contact side. Important note. 1. Normal, less than 0.05 mm. 2. Warning if, more than 0.1 mm. 3. If more than 0.2 mm, teeth crack or other problems. See this picture. The module of a gear. Module equal, reference diameter, over number of teeth. The module of a gear. The mutual relation between the module and the reference diameter, etc. is as follows. Reference diameter, D equal, M multiplication Z. Reference diameter equal, module multiplication, number of teeth. Number of teeth, Z equal, D over M. Number of teeth equal, reference diameter over module. Reference pitch, I equal, pi multiplication M. Reference pitch equal, pi multiplication, module. Then, what is the reference pitch? It is equal to the circumference, divided by the number of teeth. Reference pitch equal circumference pi multiplication D, over number of teeth, Z. Temperature measurement. Further heat sources might be related to 1. Very tight shaft seals, pinion shaft and housing. 2. General high operating temperature or rotary kiln. 3. Lack of lubricant. 4. Misalignment and therefore insufficient contact ratio, leads to partial overloading of specific areas. Temperature measurement. 1. Measuring the pinion flank temperature, during operation under load, with an infrared thermometer has proven effective, for recognizing an uneven load distribution on the flanks. 2. A temperature difference of more than 3 degrees C between the right and left side of the flank width, indicates uneven load distribution, which requires realignment of the gear drive. In this picture it is explained. Average temperature distribution, on the pinion's tooth flank. Surface roughness. 1. Polished area. 2. Scratching. 3. Scoring. 4. Initial pitting. 5. Progressive pitting. 6. Cold flow. 7. Crack. 8. Breakage. Pitting. In this picture it is explained. Initial corrective pitting. In this picture it is explained. Progressive pitting. Pitting is fatigue damage, resulting from overloading. Scoring. In this picture it is explained. Light scoring. In this picture it is explained. Moderate scoring. In this picture it is explained. Cold flow. In this picture it is explained. Spalling. If the spalling is concentrated on one end of the face width, check the alignment with thermal imaging, and correct if misaligned. In this picture it is explained. Crack girth gear. A prominent failure mode of large girth gears is tooth fracture, which is often preceded by either severe macro pitting, wear, and/or fatigue cracks. Identifying and categorizing these potential failures, and their severity enables the user to make informed decisions about replacement or flipping gearing. Lubrication. Lubrication is essential to avoid wear. 1. Continuous transfer lubrication, paddle wheel. 2. Continuous circulation lubrication. 3. Automatic spray, most used. Continuous transfer lubrication, paddle wheel. Note. 1. That sometime, paddle wheel is installed on girth gear. 2. It is important to check sump and paddle wheel regularly. Continuous circulation lubrication. 1. Lubrication to be applied uniformly. 2. Filters must be checked regularly. In this picture it is explained. Automatic spray. In this picture it is explained. Lubrication system for rotary kiln. Separate lubrication. Girth gear, pinion and main pinion bearings. 1. Forced lubrication of girth gear and pinion, with adequate lubrication unit. 2. Choice of oil lubricant viscosity, depends on teeth working temperature. 3. Oil viscosity should be higher than 300 cst, at effective working temperature of teeth meshing. In this picture it is explained. Spray lubrication system. Spray lubrication system. Spray lubrication of the gearing involves that a lubricant is atomized by pneumatic pressure, and sprayed towards the gearing so that the lubricant covers the pressure tooth flanks of the pinion, with an even and uniform layer. From the pinion the lubricant is distributed to the gear rim. The need for lubrication varies depending on the operating conditions of the gearing. Consequently, the design of the spray system incorporates automatic adjustment of the lubrication rate, in order to meet the specific requirements of the actual mode of operation. The spray system proper is available in various makes, though the working principles are basically identical. The same also applies to the supervision and control systems. For the special features of the individual spray system, reference is made to the separate instruction manual from the manufacturer. Performance test. 1. Check the spray image once a week. 2. The design of the gearing guard is such that it is possible to insert a control plate between spray nozzles and pinion to capture the lubricant discharged. 3. The plate is placed in 2 guideways on the guard, with a piece of paper glued on at either end, in order that the spray image can be recorded. 4. Proceed as described in the supplier's manual. 5. Then evaluate the spray image. The spray system design entails that the amount of lubricant supplied to the corners of the teeth exceeds the amount supplied to the central half of teeth. This figure shows an example of a stationary spray image. In this picture it is explained. Performance test. Girth gear lubrication. 1. An important factor for operational reliability is as perfect spray pattern without any gaps. The lubricant must be distributed evenly over the entire height and width of the tooth flanks. 2. Periodic checking of the spray pattern, at least once a month, is an essential part of maintenance. In this picture it is explained. Alignment of spray system. Preferable orientation of a spray nozzle, x equal 200 positive or negative, 50 mm. In this picture it is explained. Arrangement of nozzle plates. Arrangement of nozzle plates. 1. The spray nozzles should not be installed in an upward direction. 2. When determining the position of the nozzles and checking spray pattern, safety comes first. 3. For operation reliability, the most critical factor is the duration of the individual spraying pulses. 4. Shorter and more frequent spray cycles. Thank you for watching, and I hope these courses are helpful to everyone. Subscribing to this channel Cement Industry Courses would be appreciated. Thank you.